show one example for the clinic. So out there, maybe some other. So you know what actually these three loci count for what part of genetic part?
In the Shed's disease?
Yeah.
What component, what percentage?
Genetic.
It's a good question, and we haven't gotten that far in terms of being able to say what percentage of the genetic component is due to the genes that we've identified. But certainly if one takes the precedent of, for example, Crohn's disease, where some 30 genes or more have been identified having similar magnitude of effects for the relative risk, still not even half of the genetic load is explained. I think that there's a lot more to go, and certainly we're thinking about larger studies with greater power in order to find those additional factors. And then, of course, there's the possibility of rare variants as well, for being part of the genetic load.
Let me invite everybody again to reception in the library, and let's thank our speaker again for an elegant presentation.
Good afternoon. I'm Jeremy Berg, Director of the National Institute of General Medical Sciences, and I would like to welcome you to our annual DeWitt Stetson Jr. Lecture. Our growing understanding of the complexity of biological systems presents one of the great challenges in modern biomedical research. We're all used to seeing figures with arrows linking genes, proteins, or signaling molecules to describe regulatory networks or biochemical pathways. Today's speaker, systems biologist Peter Sorger, will guide us through approaches to help us try to understand the complex dynamics of living systems. Indeed, these approaches may represent what it means to understand such complex systems. Dr. Sorger uses computational methods along with bench experiments to develop systems-wide models of cell function that still contain information about how individual cell components behave. These models address how it is that cells with the same genes in the same environment can respond differently to biochemical cues or drugs. Dr. Sorger received his undergraduate degree from Harvard and a PhD from Cambridge University, both in biochemistry. He conducted postdoctoral work at the University of California, San Francisco, where his mentors were Andrew Murray and Harold Warmus. Dr. Sorger has been a faculty member at MIT since 1994, and in 2006 also joined the faculty of Harvard Medical School. I refer you to the program for further details about Dr. Sorger's background and affiliation. I'm proud to say that NIGMS has supported Dr. Sorger's research since he started running his own lab in 1994. Before I invite Dr. Sorger to the podium, I'd like to take a moment to tell you about the highly regarded scientist for whom this lecture is named. Dr. Stetson spent most of his career at NIH serving in two institutes in the office of the NIH director. He was perhaps best known as NIH Deputy Director for Science, but prior to that time he served as the third director of NIGMS. In recognition of his many contributions to NIH and the scientific community as a whole, Dr. Stetson has the rare distinction of having two NIH entities named after him. This lecture is one of them, and the other is the DeWitt Stetson Jr. Museum of Medical Research, which was dedicated during NIH's centennial in 1987. Dr. Stetson died in 1990. And now on to Dr. Sorger's talk, which is titled Measuring and Modeling Cell Death Decisions of Single Cell.
Well, thank you very much. It's really a great pleasure to be here at the NIH, and I'd like to thank Jeremy for this introduction, as well as really to start off by acknowledging the enormous amount of help that I've had from NIGMS and NCI, and the many people who've had a big impact on on my research, people like Jim Dethridge and Jim Anderson, who have impacted both the early phases of this, and Jerry Lee and Jim were jointly funding the Cell Decision Process Center, which was one of these P50 centers in systems biology that let us start on the science I want to tell you about today. So the basic biology, I think, is familiar to all of you, and it has to do with this issue of how it is we control the spatial and temporal distribution of life-death decisions. And in this sort of simple and sort of canonical example of the development of a chick limb or how it goes wrong in a human in syndactyly, we're reminded that most of the morphological structures that we have are formed not only by the correct proliferation, but also the correct death of many cells. And in the case, for example, comparing a duck to a chicken, you have the same proliferation of the digits, you just have a completely different death program going on in the interstitial space. So we've been particularly interested in problems in apoptosis and proliferation as they apply both to cancer and immunity. And I'm going to tell you a story today that sort of lies right at the intersection between those two things. And specifically, what I want to tell you about is the biology of the trail-like molecule, which is a CNS-type human necrosis factor type molecule that binds as a trimer specifically to receptors in the transmembrane domains of a large variety of different cell types, and in that context is able to trigger a classic caspase-dependent apoptosis cascade. And that results, this binding of the trail to its receptor then results in the activation of initiator caspase, so-called caspase 8 and 10, created by this picture here. That then triggers the next step in the process and eventually will go on and kill the cell. And the biology of these molecules is really very interesting. They're part of a fairly complex process of immune editing, which I simplify rather grossly in this slide, but to give you the sense that one of their critical functions, and one that's now being exploited therapeutically, is the ability of these molecules to selectively kill tumor cells. And it's thought to reflect the activity of both NK cells and cytotoxic T cells in recognizing tumor-like cells and then engaging through here a juxtakine mechanism, both trail and its closely related fast-type ligand. Now, one of the things that got us interested in a few years ago is that this class of molecules, trail-like ligands as well as agonist antibodies, are now in fairly active clinical development by a variety of large and small pharmaceutical companies. And these are, as this little review would imply on another one of these network pictures, being combined with a wide variety of targeted and classic cytotoxic chemotherapies, and all attempting to exploit this property of the trail-like ligand, that it will kill tumor cells relative to normal cells. And as with so many of these molecules, I pulled this out of a few recent reviews, what of course happens is that they've been efficacious in a small subset of tumors in some patients and not in many others. And much of the clinical development of this sort of first-in-class category